Hi everyone, welcome to this new lecture of hydraulic machines. In this lecture, we'll discuss a concept of jet propulsion of ships when inlet orifices face the direction of motion of the ship. So this is the second category of this jet propulsion of ship. In the first category, we have seen when the inlet orifices faces perpendicular to the motion of the ship. So in the previous lecture, we have already discussed that concept actually. So in that condition, actually the ship is like this, and in the ship, like suppose this is the ship is there, and here the water used to come like through this. So this is the suppose middle of this ship, and this is the pump here we have settled, and through this the water used to come out from the pump. So here the jet motion or the ship motion is in this direction, okay, and the water is to enter through this orifice. This is the orifice and this is the orifice. Through this orifice the water is to come inside to this ship, you can say, and this is the centrifugal pump which is there. So this one like it is right angle, you can see it is right angle to the direction of ship. Now here the condition what we have taken, the ship is moving in this direction, as well as here also the orifices are taken at this point. Okay, this is the inlet of the orifice, these two are the inlet of the orifice. So through this orifice the water used to goes inside the inside the ship, and as usual here also one centrifugal pump is installed. So you can say as we know that pump how it is to works, so it used to have a that suction valve is to there, and from here again it used to one delivery valve or delivery pipe, and this is suction pipe. So this is the pump. In this condition you can say like this is the suction part is there or inlet of the pump, and this is the outlet of the pump, or you can say delivery pipe here, or the water is moving out from this pump at this point. So this is actually the jet of water which is coming out from the pump. This is actually the jet of water which is coming out from the pump with a velocity of v, and that is also called as stern. Okay, so in this condition we need to find out what is the force exerted, what is the force exerted, and what is the work done happened, and what is the efficiency of this. So these are the three things we have calculated in our last lecture for when the condition was taken for this. But here as you can see the direction of motion of the ship and the inlet like orifice of the inlet both are in the same direction. Previously it was like perpendicular, you can see this is the orifice inlet, so this is perpendicular. Now it is the same direction, is parallel, we can say. So a ship is having an inlet like at the orifice which is facing towards the direction of the motion. For this condition, the propelling force, and the work done, this propelling force and the work done, okay, this will be equal to what we have got for this condition. So in the first condition what we have identified, it will be the same, so it will be equal to the first cases. Okay, so here what will be the different, so different things will be like the energy required to supply it. Here the different things will be the energy required to be supplied by the pump, okay, supplied by the pump. So this point will be different. As you can see that in this case the water enters with a velocity which is equal to the velocity of the ship, because this is the velocity of the ship u. So the velocity of water which is entering here, that also will be equal to this u. Okay, so that is the velocity of u we can consider. Okay, so the expression we need to find out the energy required to be supplied by the pump or by the jet, we can say. So now before going to find this terminology, I'll just recall this force exerted what we have identified in our last lecture. So let me write the force exerted, or you can say the net force exerted by the jet. So here we know that F equal to m into A, and this one again we can write in place of m, I can write this is rho into V, this is density into volume, into acceleration I can write this is change in velocity with respect to change in time. So this volume with respect to time, that means you can say discharge. So this one again we can write rho into discharge, that is Q, and this is dV, change in velocity. Again this one we can write in place of discharge, I can write rho into A into V, area into velocity. This is discharge formula. And in place of dV we can write this is V2 minus V1, or final velocity minus initial velocity. So this terminology we can write here. So this is actually what also we have derived in our previous lecture. So we can write the force exerted in the x direction, this equal to, again this one rho into A, rho is nothing but density of water, area of the orifice we can write here. And next is in place of V, what is this V? This V we need to consider actually the relative velocity, because the jet of water which is coming out from here, due to this jet of water, the impact of jet of water, the ship started moving. Because this concept actually, let me remind you, this concept is working based on the Newton's third law of motion. Okay, this is Newton's third law of motion, which says that that every action is having equal and opposite reaction. Okay, so what is the action is there, this velocity which is coming out, it's giving a reaction, and due to this reaction this ship started moving forward direction. Okay, so if it only jet of water is there, then we could have considered only V. But here jet of water also moving, this ship also started moving, so we need to consider a relative velocity. So relative velocity concept already I told you many times. What is relative velocity? This relative velocity need to be considered between two object or two body when it is moving inside like in the similar direction, or we can consider in the opposite direction also. Okay, if suppose this is A, this is velocity A, and this is velocity B, the object the body A is moving with a velocity of VA, the body B is moving with a velocity of VB. Then what is the relative velocity between them? Then we can find out the VR equal to, we can write VA minus VB, which is more that we need to write fast. So we need to write in such a way the relative velocity of A with respect to B. In that way we need to find out. So these things already I told you previously. So when it is in reverse direction, then what is the velocity which is there, suppose VA, then here it will be there minus VB. So this one we can write VA minus VB, so VA plus VB we can write in this way. This will be minus and this will be plus. So here we can write, we need to write here VR, relative velocity. Similarly here also we can write it here like what is the final velocity and what is the initial velocity. So here again we can write this is VR minus, and initial velocity, that is U, we can consider, which is this is the velocity of the water which is coming inside here. So again in the place of VR I can write, in place of VR what I can write here, this is final velocity V minus initial velocity which is moving in this reverse direction, so that is minus of U. So we can write this is V plus U, V plus U, the same thing, like this is the velocity of fluid which is coming out and the ship which is moving in this direction. So this one again we can write this is rho A, and in place of this one we can write V plus U, this is bracket start, and here we can write this is V plus U minus U. So if you just multiply this one, or you just do some addition subtraction here, finally we can get the Fx equal to the force exerted in the x direction equal to, this is rho A, we can write this is VR. So yeah, V already I have written, so this is only V will be there, so rho A V into, we can write this is V plus U. Okay, this is our equation 1 we can give. Similarly, once you find out the force, this is actually similar to the first case also. That's why I told you initially starting this work done and force both will be same to the first case. Okay, now if you want to find out the work done, similar thing, like how to find out the work done, we know that the force exerted in the x direction into, with respect to, this is work done per second actually. So work done per second, that is nothing but, we can write force into distance per second. So distance per second is nothing but u, velocity. So again we can write fx value is nothing but rho a v u into v plus u. So this is our equation 2. Now we need to find out what is the power required. So power required also same thing, like what is work done is there, or power required with respect to kilowatt also you can find out. That will be enough. Now the next thing is we need to find out the efficiency. So what is the efficiency of the propulsion? So efficiency of the propulsion, that we know that this one actually we can write output from this pump or output from this ship, or what is the input is given. So what is the outputs we got and what is the input was supplied. So the output is nothing but, we can write this is work done per second, work done per second by the jet, work done per second by the jet. And what is the input was given to this one? Input is nothing but what is the energy was supplied, what is the energy supplied by the jet, what is the energy supplied by the jet. Initially what I have written here, this one, energy to be supplied by the pump, or we can say that is by the jet. So this one actually we need to find out. Remaining all things are same. This is only need to be identified, that what I have written here. So work done per second by jet already we have identified here, so that we can write this is output, which is the output we need to write here, work done per second by the jet. So that is nothing but, we can write here rho a, this is v u into v plus u. And what about this energy supplied? Energy supplied by the jet, that we need to write, we need to identify. So this is, let's find out energy supplied. So energy supplied by the jet, we can write this is half mv square. This is, we can write half mv square. So half mv square. Now here this m is nothing but, okay, this is mass flow rate we need to consider, the mass of water which is supplied per second. So this one will be, can be written here half m dot into v. V is here, what is the v square is there. So here also we need to consider the initial velocity and final velocity what is there. So that also we can write here. Okay, so finally let me write what is the value of m dot. M dot equal to, actually I can write this is rho a vr, mass of water supplied per second. This is vr, rho a v. M dot equal to rho a v, what we have found here previously also. Here also I have identified here rho a v in place of m. So same thing I can write in terms of this. And what about this velocity? So this is change in velocity actually. So here we can write this like v plus u square, v plus u square, because this relative velocity we need to consider here. So that is v plus u square I can write. And v plus u square on place of vr. But what about this u? U will be this one. This one again I'll write here so that you can understand more. This is half rho a vr into, this is vr square minus u square. Okay, this is our half mv square, that energy supplied by the jet or by the pump. This is the formula. Then from here we can write this Okay, this is VR plus V plus U square and minus U square. Now this value we need to put here. So let me write here half, and this is rho A, and this is V. In place of VR, again I can write V plus U. So I'll write this is V plus U, and bracket start. In place of again VR, I can write this one. Actually VR I can change it this one. One more step again I need to write. This is rho A, this is V plus U, again bracket start. This is V U square minus U square. Okay, I hope you got it. Now this is actually the kinetic energy which is supplied by the jet. Now the same thing right here. This is V plus U square minus U square, bracket close. Now if you see, this rho A will be cancelled, V plus U, V plus will be cancelled, and finally we can write, I'll write this term here, efficiency equal to, so this is separate part, this is separate part, let it keep separately, and here efficiency we can write, let keep it separately. And efficiency, if you after cancelling, you will get here like 2 into V into U divided by, here if you see, V plus U square minus U square. So this one we can write A plus B whole square, we can write, and after writing A plus B whole square, we can write here V square plus U square plus 2 UV minus U square. Okay, so now we can see U will be cancelled here, sorry, not this one. Yeah, U square can be cancelled, only V square plus 2UV. Now if I take common of V here, then V will be cancelled, numerator V and denominator V will be cancelled, and finally we can write efficiency equal to, this is 2U divided by only V plus 2U. This is our final efficiency. So this is the case when inlet orifices is in the same direction of the motion of the ship. And when it is perpendicular, in that case it is slightly different, only the efficiency part was different. Remaining, as I told you, the force and work done part is same as usual, like our first initial case. So I hope you understand this derivation. Still, if you are having any kind of doubt and query regarding this, you can give a comment on the comment box. Thank you all.